Welcome back, welcome back. We're starting another project here. If you've been watching this channel for a while, you know I like starting projects, and I've started a lot more projects than I've finished because, well, I mean, why solve your problems when you can just create new ones?
It is as intricate and precise as a well-played game of chess.
As you've guessed from the title, and some of you have guessed from the previous video where I mentioned there may have been a new project starting, we're trying to make Cubane. More specifically here, we're trying to make this molecule up here, which I've drawn terribly. I've drawn all this terribly. Cubane 1,4-dicarboxylate. So the cubane with those two carboxylate groups on the either side of them. That's our end target molecule for this synthesis. That's what we're trying to do. I might switch over to the other camera because people enjoy the other camera more than my hand waving in front of the camera all the time. So before we dive into the synthetic plan, I think it should be asked, why are we making this? And well, very quickly, it's very nice. I mean, people like making the cubane without the carboxylate groups on it, just because it's a very cool molecule to look at. People thought it was impossible to make a molecule like this until a group in the 1960s, of course. Fuck me, I love the 60s. And that was a really great demo. The fact that you can really synthetically plan something and actually make it happen, it was very cool. I'm interested in it from an energetics point of view. Obviously, there's the absolute classic explosive octonitrocubane and heptanitrocubane. They are considered the best secondary explosives, but they're also like the hardest thing to make ever. So even if we get it to here perfectly, actually getting to the octo or heptanitrocubane is impossible. We're not going to be able to do that. It's impossible for basically all labs to do, so no one's really made it and actually tested it in the field. So its claim of being the best explosive ever is kind of very easy to make when no one can test it out very well. However, just because octonitrocubane is too impossible to make doesn't mean it should discourage us from trying to make other energetic cubane molecules. Really, there is some interest in making energetics out of cubane more and more now, as this molecule has kind of become commercially available in recent years. It's still obviously expensive, but it's sort of getting to the point now where people are even using it in like pyrotechnic compositions, because you've got a really energetic source of carbon here. In our cubane dicarboxylate, we've got, 10 carbons, so 8 in the cube and 2 in the carboxylate groups, and 4 oxygens. And if we consider a similar molecule with a very similar molecular formula, but instead we've got benzene group and we've got 2 methyl groups and 2 carboxylate groups, so we've still got the same number of carbons, same number of oxygens, but this cubane molecule is much more energetic. Those 8 carbons are forced into awkward bond angles. You get lots of energy out from that strain. If you have this with an ideal mix of an oxidizer, going from an unstable molecule all the way to something stable, whereas here this is quite stable, so you're not going to get a whole lot of energy out. So even though you're going to the same amount of carbon dioxide, the same amount of carbon at the end of the reaction, you're not starting from something very unstable, you're starting from something stable, so you don't get a whole lot more energy out. When you have only a limited amount of stuff to work with and you want the most energy out per gram or something like that, suddenly cubanes become very attractive because they're a hydrocarbon source that's very energy dense. So how can we make it? How are we approaching this? Traditionally, this is thought as being way too hard, and that's because most people reference the classic 1962 synthesis, which uses some quite exotic reagents and stuff like that. But over the years, it's actually been refined, and different papers come out and they refine each step. But there's really 2 papers, one in the late 90s and one in 2011. They're both actually from Victoria in Australia, from the CSIRO. So yes, Australian chemistry. And what they're trying to do is they're trying to make it an approachable synthesis. First one came out in the 1990s, which is a lab scale synthesis. And the one in 2011 is a pilot scale synthesis. So what they're trying to do is they're trying to say, how can we make 5 kilos of cubane at once? And that's the sort of approach that, like Ligma Aldrich will take on. So then they can start selling it. They can make 500, not 500, but like 5 kilos in a batch. So that drives the price down, makes it commercially available for everyone. So what I've done here is I've drawn up the synthetic pathway from basically from the 2011 paper, and in blue there's some slight changes from the 1997 lab scale paper. We're going to obviously be doing it on the lab scale. We're not going to be doing it litres and litres scale, because that pilot scale paper is quite threatening to read actually, when they do like, oh yes, just adding in 2.3 kilos of sodium hydroxide and 8 litres of methanol. You're kind of like, ugh. But what you'll notice about the synthesis is first of all, when you first glance at it, it looks really complicated because you've got these weird structures and that sort of thing, and what's going on here, and my drawing really doesn't help. But really, when you start looking at it closer, you start realizing that, hey, look at the reagents they're using. There's bromine, dioxane, sodium hydroxide, methanol, sulfuric acid, and hydrochloric acid, and that's about it. Most complicated reagent they're using really is the solvent dioxane here. There's nothing that they're using that I don't already own and is not really an approachable home lab chemical. So the pilot scale paper starts from this diether here, but the lab scale paper from the 90s starts one step back at this cyclopentanone. And you might remember that I made cyclopentanone a couple of weeks ago. I don't know how long, however long ago. I'm sure it was more than a couple of weeks at this point, from adipic acid. So this step we've actually already done. So we turned adipic acid, which is a food preservative, into our cyclopentanone, and then using the cyclopentanone, we react it with ethylene glycol to form this diether here. Then bromine to put these bromine groups on here. This is actually a Diels-Alder reaction because we're pulling off these bromines, which kind of forms these double bonds here, and so two of these molecules will react together in what's a Diels-Alder reaction, which is, a real classic, exam question type reaction. And then sulfuric acid just to pull some those really protecting groups off. And then what's interesting here is we've got a UV reaction. Now, I've never done a UV reaction. There's been quite a few requests for one. We do some photolysis here, sort of cyclize the molecule a little more to start forming a cube. And then they're just using sodium hydroxide and methanol and some acids, and they form the dimethyl ester of the carboxylate. They do that just for purification. Apparently this one's very easy to purify because they can purify it by sublimation. Once you purified it, you can just cleave the ester groups and you've got your final product. So it's quite different than the 1962 synthesis. It doesn't start from adipic acid. It starts, I think there's a double bond here, which is much less approachable because we can't just make that from a food preservative that I got from Amazon. Really, it's actually strangely approachable. There is, of course, many small catches, little subtleties, things that we're going to have to try, new things that are really going to test us out in the lab here. For example, in going from here to here, there's a vacuum distillation, which I'm not sure we can get around. Haven't done a vacuum distillation. This UV source here wants a UVB line, so we're going to have to get a mercury lamp, but like a medium pressure one, or maybe just filter it out with some borosilicate and just use a 311 line or so. I don't know. Anyway, all of these steps are quite interesting, but amazingly, it's actually quite approachable. And so it'd be really great to have just a few grams of this final product here, this Cubane, and then we can think about what we do afterwards. That being said, I haven't completed it yet, or I've done one step, so it could all be a complete disaster, and I might never finish it. If you have any suggestions, I've obviously linked the two papers in the description, and as well, obviously working towards a main channel video where we look at some Cubanes, and that probably won't be made for a long time, but of course the main channel has a Patreon if you want to check it out there. But always, thanks for watching this video, and I always look forward to your suggestions in the comments for each step. There's obviously going to be quite a few videos coming along on this, but I'm really looking forward to do some really cool organic chemistry. Hopefully it doesn't all go bloody yellow or tar up. I think it's all going to go yellow at every step, knowing this sort of organic chemistry. But can you feel my enthusiasm? I think I can. I feel like I'm enthusiastic. Yeah, I'm really excited.